Well, I would like to say with regard to the Nobel Prize, I got the call from Sweden at 2:15 in the morning on October 3rd of 2 years ago. And the voice at the other end said, it won't surprise you that this prize is being awarded to you, Rainer Weiss and Barry Barish. And I said, I'm not surprised, but I'm very disappointed. I was disappointed because the prize should have gone to the entire team, including as major contributors the people here at Cardiff who made huge contributions. This could not have happened successfully without the combined efforts of a very large number of people. And the Nobel Committee has not yet figured out that they have an obligation to educate the world about the power and the importance of collaborations on certain kinds of science and technology, and that this can't just be done by a handful of people. So anyway, that's my attitude about it. I'm happy to be an icon for the team, but it really was a huge team effort with Cardiff playing a major role. So what I want to do is tell you a bit autobiographically about my career. I arrived at Princeton University in 1962. That's more than half a century ago. It's, if I count on my fingers, it's 57 years ago. And I went there to do PhD research, to learn how to do research from John Wheeler, who was a very inspiring man, who was the guru in that era, teaching us about black holes and about neutron stars, gravitational waves, Einstein's relativity theory, and all the weird things that might happen due to warped space and time. What I learned from John was, this is the way I describe it today. I didn't use these words at that time, but it's the basic idea, that there is a warped side of the universe, or that there probably was a warped side of the universe. We weren't sure at that time. By which I mean objects and phenomena that aren't made from matter like you and I, but instead are made from warped space and warped time. And examples about which we speculated, but we really had almost no observational data to say whether the speculations were correct or not, were black holes. That was totally speculative at the time. Gravitational waves, totally speculative. The Big Bang singularity in which the universe was born, which consists of, was made from quantum mechanical warped space-time, to use a buzzword phrase. We did have observational data for that, but it was far from clear whether there really was a Big Bang at the beginning or whether something else was going on at the very beginning. Wormholes for rapid interstellar travel, time travel, these were all things that we speculated about that you could see in the equations that Einstein gave us, called General Relativity equations. In this lecture, what I'd like to do is tell you what we have learned in these past 57 years about the warped side of the universe, going from this being almost pure speculation to what has been found to be absolutely true, what is still speculative, what is likely to be wrong. So that's where I'm going. And what I'm going to tell you is from the combined work of a large number of people again. I have contributed, and these are the things that I have been particularly interested in during my career. But it really is, again, the work of a community of a large number of really great men and women who took upon themselves to study these kinds of phenomena. So let me begin with black holes. A black hole is the quintessential example of an object that is made from warped space-time. As an example, if you have a black hole and it's sitting here, it's absolutely black, it's spherical, or if it's spinning, it's a flattened sphere. And its diameter is far larger than its circumference. If you look at that, you say, well, no way. That diameter is clearly smaller than circumference. The ratio is 1/pi. But in fact, that's not true. The diameter of a black hole really is huge compared to the circumference. And the way that I like to explain this is by a little analogy. If I take a rubber sheet, a child's trampoline, say, put it up on tall poles, and then put a very heavy rock at the center, the sheet will bend down like that. Now, pretend you're an ant. You're a blind ant, so you don't know what's going on. You don't see the universe out here. All you know is this rubber sheet. This rubber sheet is your universe. But you've studied physics at Cardiff University or engineering, and so you know it's an interesting thing to measure the geometry of your universe. And so you go walking around here, and you measure the circumference, and then you set out to measure the diameter, and you walk, and you walk, and you walk, and you walk, and walk, and walk. It's a very huge diameter. The diameter is huge compared to the circumference. And you say to yourself, well, obviously, I live in a warped space, a universe where space is warped. It's not like a flat sheet of paper. And that is precisely a precise analog of a black hole. All I do is change the labels. So now I'm looking at an equatorial slice through a black hole, something that you would have thought was a flat plane through a black hole, but going right through the equator, cutting the black hole in half between top and bottom. But in fact, it is warped in just the same way as that rubber sheet was warped. Warped in what? Well, not in our universe, obviously. If it is in our universe, then you would expect it to have the usual Euclidean geometry. So it must be warped in some higher dimensional space, which physicists sometimes call the bulk. And so what I'm showing you then is a two-dimensional surface of our universe, but you're looking at it as it is warped in the higher dimensional space. And then the diagram is just the same as what I showed you before. Now, the thing that most people know about black holes is that if you fall into it, you can't get out and you can't send signals out. So here I am. I'm a little two-dimensional Kip. I'm falling into the black hole. That means I'm on the surface of this sheet, two-dimensional sheet. And I'm sending microwave signals out to you to tell you what I am experiencing. There's a surface of the black hole that we call the horizon. When I fall through the horizon, after that, I am pulled inexorably down to something called the singularity at the center. But also the microwaves that I'm trying to transmit to you, they are also pulled down toward the center. They cannot get out. And so the horizon is a horizon in the same sense of the horizon that we don't see beyond if we're sitting, say, out in the desert somewhere. But this horizon is something that you can't see into. You can't see from the outside in. But if I'm in here, I can see you. I can look out and see light that's coming down to myself. Now, the black hole then is made from warped space. Things can't get out of it. But one way to understand that things can't get out of it is because of warped time. Time slows as you near the horizon of a black hole. And so if you're hovering here and not falling through, the closer you get to the horizon, the slower time is flowing compared to what you see very far away. In the movie Interstellar, for those of you who saw it, Cooper goes down near the horizon of a black hole. He's there for a few hours, comes back, and his daughter has aged from age 11 to becoming a great theoretical physicist of age 28. It was really nice to see Jessica Chastain playing a great theoretical physicist. And in fact, at the world premiere of the movie, the only thing she talked about was the fun, the joy of being a theoretical physicist. So anyway, so you see this in the movie. If you fall through the horizon, then time doesn't simply slow down. Time flows in a direction you would have thought was a space direction toward the singularity. And so that's one reason you can't get out. It's because you cannot move backward against the local flow of time. You're just dragged by the forward flow of time or the downward flow of time down to this singularity. I'm not going to talk about the singularity in this lecture, but if you want to ask me questions about it, I can tell you about it in the question period. I want to focus on things outside the black hole. But first, I want to tell you there's one other aspect to the warping of space and time around a black hole. That's a whirling of space. If the black hole is spinning, then it drags space into a whirling motion like the air in a tornado. And that whirling motion is absolutely inexorable. If you're near the horizon of the black hole, there's no way you can remain at rest relative to the distant stars. You're dragged around and around at very high speed around the horizon of the black hole. I should remark the horizon here is drawn as a circle, but remember I've removed one dimension. I'm showing you a two-dimensional slice of the black hole, so that horizon is really a sphere when I restore that dimension. So you have a warping of space, you have a warping of time, and you have a whirling motion of space. This is a precise depiction of what general relativity says is the warping of space-time around a fast-spinning black hole. This is the precise shape of space. You go out very far away, and this becomes flat, and you're out, say, near Earth. Down here, you have a very deep funnel. Down here, the horizon is this black circle. Remember, it's a sphere when I restore the other dimension. The color coding is showing you the slowing of time. Where it's yellow, time is flowing at 10% of the rate that it flows at back here on Earth. And where it's black, time is slowed to a halt. And the white arrows show their length is proportional to the angular velocity of dragging of space into motion. And so it's a high angular velocity near the black hole and lower farther away. Just like if in a tornado, it's a faster speed near the core of the tornado and much slower farther away. Now, what produces this warping of space and time? Well, Einstein tells us that the warping of space and time is produced by huge amounts of energy or mass. So where is the energy here? There's no matter. So there's no matter providing you energy, no matter providing mass. Where is the energy? The answer is the energy is contained in the warping itself. If you think about that rubber sheet and you push this rubber sheet down, you have to do work to push it down. It may be very stiff. You have to do a lot of work. You're putting energy into the stretching of the rubber fabric. In the same way, there's an enormous amount of energy in the warping of space and time here. And it's that energy that produces the warping. So the black hole is held together in technical terms by what we call a nonlinear self-interaction of the black hole. The black hole's energy of warping produces the warping. It is what we sometimes would call a gravitational soliton, to use a technical phrase. There's another point of view to take on this dragging of space into whirling motion. If I take my wife and I hang her just above the surface of a black hole, or if she falls through, it doesn't matter either way. This is a painting by a great artist named Leah Halloran, who's good enough. She has had one-woman shows at the Guggenheim in Spain. And she and I are doing a book together right now. Her paintings about these kinds of things and my attempts at poetry. That's what you do when you get to be 80 years old and you're a physicist. You write poetry. Okay, so anyway, her feet are dragged around faster than her head. So as she looks down, she sees her feet whirling around counterclockwise. And if her feet look up at her head, her feet will see her head going counterclockwise. You can understand this by imagining taking a wet towel and you wring the water out of it. And think about it. If your left hand sees your right hand going counterclockwise, your right hand will see your left hand going counterclockwise. So there's a counterclockwise twist of space at the north pole of the black hole and a clockwise twist of space. We call these vortices. Counterclockwise vortex sticks out of the north pole. A clockwise vortex of twisting space sticks out of the south pole. Now, I probably won't have time to tell you in any detail about it, but we have learned in recent years through computer simulations that when black holes collide and merge, these vortices fight with each other and behave in really weird ways. So there's a great richness to the warping of space and time around a black hole. It even has things sticking out of it like my arms that are made strictly from twisting space, which can behave in really weird ways when black holes collide. Black holes in our universe. What do we know now after 57 years? We know that there are roughly 10 million black holes in our Milky Way galaxy alone. Astronomers have begun to make a census from their observations. There are about a billion, 10 to the 18 black holes in the universe as a whole. An unbelievably large number of black holes. The masses of the black holes range from about 3 times the mass of the sun. All that means when I talk about mass is the gravitational pull of the black hole if you're at some fixed distance away from it. is the same as the gravitational pull of 3 suns. And that's how we measure mass, actually, in astronomy. You always measure the mass of a star by its gravitational pull, the mass of the Earth, the mass of Jupiter by its gravitational pull. So the masses of black holes range from 3 times the mass of the sun to 20 billion times the mass of the sun. Their diameters are proportional to their masses. They range from 10 kilometers to 100 billion kilometers. So tiny black holes, smaller than Cardiff, to black holes that are as large as the solar system. What does a black hole look like to your eyes? Well, suppose that I have here, and I'm looking then in from the higher dimension from the bulk, I have a star here, and it sends light to a camera there. And the light rays can travel through this warped space around the black hole along this light ray. That's one light ray that goes to the camera. This is the closest thing you can have to a straight line that reaches from the star to the camera. Or along that light ray. Or there's a light ray that goes down, whirls around the black hole once, and goes up to the camera. And there are light rays that go down and whirl around several times and come up to the camera. So there are a large amount of images. The 3 images, in this case, are shown here. Here's the shadow of the black hole. Maybe you can see it better on the side here. This doesn't have as high a dynamic range in the central screen that what we have here. So there's the black hole shadow, and here are the 3 images carried by those 3 light rays. Now suppose that you have a huge number of stars, and the black hole is just sitting here in front of the stars. They're all very far away, and it's creating a shadow just like this. Then what does it look like? Well, this is from a computer simulation that was done by Oliver James, who's the chief scientist at Double Negative Visual Effects Company in London, that made and got the Academy Award for the visual effects in the movie Interstellar. And Oliver used equations that I gave to him, fed to him, to compute what this would look like if you're looking at this black hole in front of a large number of stars. The camera is going to move around the black hole slowly, and so naturally the pattern of stars is going to change, and it's quite interesting to see how it changes. This place where the stars appear to be moving rapidly is called an Einstein ring. There's another Einstein ring down here. In fact, there's a whole range of an infinite number of Einstein rings snuggling up to the edge of the black hole. And if you look in here, you see images, 2 images of a star. Say down here, it's easier to see. I'll back up and start over again. You see images annihilate in pairs. You see them created in pairs. So you just have to look closely. It's easier to see down in here, but you see 2 images come toward each other and they annihilate each other. You see there's no image, and then suddenly a bright spot appears in the image, and you have two images that go flying apart. How does that come about? Well, that's something that we explored, that I explored together with the team that did the visual effects for the movie Interstellar using this computer code. And now I'm going to say something for the benefit of the mathematicians and physicists in the audience. The rest of you have to just let me indulge myself for a few minutes with some jargon, okay? There won't be much of it, but each Einstein ring is the image of the intersection of the celestial sphere, the place where the imaginary celestial sphere very far away where all those stars are sitting, with a caustic of the camera's past light cone. So there is physics jargon, but it means something to some mathematicians and physicists in the audience. When a star on the celestial sphere passes through a caustic of the past light cone, 2 images are created or destroyed. The caustics on the celestial sphere look like diamonds, distorted diamonds. And when the star moves into the diamond, 2 images appear. And when it moves out of the diamond, 2 images annihilate. And so there's really interesting mathematics underlying these weird patterns that you see. Okay, having indulged myself, I'll move on. If you want to read about it, the physicists or mathematicians, the only paper I've ever published in the journal Classical Quantum Gravity, just look up my name in that journal and you will find it there. Okay. But that's not what the black hole looks like in the movie Interstellar. This is what it looks like. And why is it so different? Well, the answer is that the black hole in the movie Interstellar is surrounded by a thin disk of very hot gas that's really bright. It's so bright that it outshines any of the stars, so you can't see the stars. And a light ray from the back face of the disk going to the camera is pulled by the warped space-time and by black hole's gravity down to the camera like that, so the camera thinks that the upper back face is up here. So that explains this piece of the image. And the bottom of the back face, a light ray gets bent as it travels to the camera. And so the camera thinks the bottom back face is down here, and so that explains this part of the image. And then here is a light ray coming from the top face of the disk. The camera is just above the plane of the disk, and so that just comes directly out, and that produces the crossbar. So it's a very simple explanation, but really quite startling to see it come out of the computer simulations when we saw this. Though this was actually predicted several decades ago, I think in the 1970s, by Jean-Pierre Luminet in France. But I had forgotten about the prediction, and when I saw this coming out, I was just amazed. It came out when I was working on the movie with my friends at Double Negative. Now, in fact, astronomers have recently, just last April, observed a disk around a black hole, or hot gas around a black hole, and observed the black hole shadow. And they did this using something called the Event Horizon Telescope. They combined the data from many radio telescopes worldwide, ranging from Greenland in the far north down to the South Pole, and from Hawaii to the Americas and all the way over to Europe. And all the data from all these telescopes were combined together to create something that was effectively a worldwide size telescope by a team of 400 scientists and engineers at 100 institutions, led by Shep Doleman at Harvard. And they succeeded after about 10 years of hard work in imaging the black hole at the center of a large galaxy near our own called M87. And this is the image that they got. And from the size of the shadow of the black hole and knowing how far away the black hole was, how far away this galaxy is, they could infer that the size of the mass of this black hole was 6 billion times the mass of the sun, a very, very heavy black hole. Okay, now let's look. This is the image in the movie Interstellar. This is the actual image that was actually made by the radio astronomers. And they're not quite the same. I've had a number of people email me say, gee, you really got it right. We didn't get it right at all. There's no crossbar here. And it's brighter on one side, and we're not brighter on one side there. So what's going on? Well, here is one way to understand what's going on. Oliver James, my friend at Double Negative, made this little movie to explain one way this could happen. So the camera for the movie Interstellar is near the plane of the disk, and so that's what it looks like in Interstellar. But we're going to move the camera up to the North Pole and see what happens. It's pretty obvious. You lose the crossbar. And then you blur things out, because the radio astronomers don't have very good angular resolution. And so you get this, but what you don't get that way is the bright edge. So how come the bright edge? And the answer is that, in fact, there should always be a bright edge, even in the movie Interstellar, because the gas on one side of the black hole is moving toward you, and there's a Doppler shift, so it's shifted to become more blue, but much more intense than the other way. And so why isn't that there? Well, I had discussions with Christopher Nolan. He was the director of this movie. He said, look, Kip, you have to take account of the human eye. And if a human is looking at a very, very bright source of light, they can't distinguish between how bright it is and it being somewhat dimmer on the other side. And so we are going to make it the way it would look to a human eye, including all of the failings of the human eye. And also, this was another important remark that goes into that image. They did include the scattering of light in the lenses in the IMAX camera. And so there's a big glare around here because the light goes into the IMAX camera and gets scattered inside the IMAX camera. And so what you see in the movie is the way it would appear to you if you were looking through an IMAX camera with the human limitations of the eye. Now, there's another difference, and that is that, in fact, the explanation for this is probably not simply that you're looking from the North Pole, but in fact, the flowing gas here is probably not even in a thin disk. It's probably swirling around in something that is not a thin disk, and it's what we call optically thin. But that's a technical remark. But anyway, that gives you some sense of what black holes look like. And so I wanted to move now on to gravitational waves. Albert Einstein in 1916 predicted gravitational waves. What he said using his relativity equations, which he had just formulated a few months earlier. He said if a gravitational wave propagates into the screen here, what it's going to do is stretch and squeeze space. So space is stretched horizontally and squeezed vertically, and then a moment later it's stretched vertically and squeezed horizontally. And another way to say it more technically is that if you have a little inertial reference frame over here and a particle at rest in it, the particle will always remain at rest in it. You have an inertial reference frame over here, the particle will always remain at rest in it. But the inertial frames will move back and forth relative to each other. And so the particles which behave inertially, they have to move back and forth with respect to each other. And that's the more precise meaning of a stretching and squeezing of space. So let's watch space stretch and squeeze as depicted by a bunch of particles, each of which is moving inertially as the gravitational wave passes. They're all at rest with respect to each other before the wave arrives, and they stretch and squeeze. Now, Einstein, when he predicted these gravitational waves, he also said, in effect, it wasn't just as starkly stated as this, but basically he said in this technical paper, these waves are so weak that it's unlikely humans will ever be able to detect them. But in fact, we have. But it took 100 years, and it took major changes in our understanding of the universe and in technology. Now, there are only two types of waves, according to the laws of physics as we understand them. Only two types of waves that can be created in the distant universe and propagate to Earth, bringing us information about what's far away. Electromagnetic waves, that is, oscillating electric and magnetic forces. This includes light, radio waves, X-rays, gamma rays. These all just differ in the wavelength, or equivalently the frequency of the waves, but they all are electromagnetic, oscillating electric and magnetic forces. And it was Galileo 400 years ago who built a small optical telescope and pointed at Jupiter and discovered the 4 large moons of Jupiter, and thereby he created electromagnetic astronomy as we know it, astronomy done with instruments, telescopes. Gravitational waves, our goal in the project that Bernard Schutz and I and a large number of people in this room who are in the gravity group here at Cardiff, our goal was to do with gravitational waves what Galileo did for electromagnetic waves. That we wanted to create gravitational astronomy by building an instrument and pointing at the sky and seeing gravitational waves coming in from something. Now, gravitational waves are made from the same thing as black holes. They're made from warped space, and as a black hole is made from warped space, also a black hole also has warped time, but a gravitational wave is basically warped space, but there's a little more to it than that. But it is made from warped space-time, just like black holes are, and therefore gravitational waves are the ideal tool for exploring the warped side of the universe. Electromagnetic waves are produced by oscillating electric charges. But gravitational waves are being made from warped space-time. They are produced by things like colliding black holes that have no electric charge, but that are made from warped space-time, just like the gravitational waves. It was Ray Weiss at MIT, a good friend of mine because we were at Princeton together. He was a postdoc and I was a graduate student before this, in 1972, who proposed the kind of gravitational wave detector that we have built and had success with in LIGO. This was his original version. I'll tell you about an improvement on it in a moment. You're looking down on it, so these are 4 mirrors that hang from overhead supports, but overhead is pointing to you. And so when a gravitational wave comes along, these are pushed apart, those are pushed together. At the next half cycle, these are pushed apart and these are pushed together. And what Ray said is to send a laser beam in, split it in half, send the light through a small hole here, and bounce it back and forth inside this cavity. Similarly, bounce that back and forth, and then recombine the light. When the gravity wave shortens the separation between these mirrors, that means that the light that went in this direction travels a shorter distance now than the light that went in that direction where the mirrors are pushed farther apart. So when the light comes back and interferes, it turns out through some physics that many of you will know about, that the interference of that light causes a change in the intensity of the light going in this direction. This is where we read out the signal. So this is what he said is how we should go about building a gravity wave detector. He called it a gravitational wave interferometer. Now, I looked at some numbers because I had been thinking about gravitational waves quite seriously as a theorist and about their sources already for a few years in 1972. And I, together with my PhD mentor, John Wheeler, and another former student of Wheeler's named Charles Misner, we were just sending to the publisher a textbook called Gravitation at the time that I heard about Ray Weiss's idea. So I thought we need to include something about this idea in this book. Then as the last minute, as we were sending this to the publisher, I looked at Ray Weiss's idea and I thought he'd gone crazy. It didn't make sense. And so I'm a gentle person. I don't like to lay it on the line when a friend of mine seems to have gone crazy. And so I just simply wrote in there, this idea is not promising. And why did I think it wasn't promising? Well, the key issue is that the strength of the waves that we were expecting was the change in separation of the mirrors divided by the actual separation, about 10 to the minus 21. That's a tiny number. If you multiply 4-kilometer separation here, which is the separation that we have in LIGO, by 10 to the minus 21, you get 10 to the minus 17 meters. And so how big is that? Well, you begin with 1 centimeter. You divide by 100, you get the thickness of a human hair. You divide by 100 again, you get the wavelength of the light that Ray said he wanted to use to measure the motions of the mirrors. Divide by 10,000, you get the size of the atoms in the mirrors that are reflecting. So that's the size of the minimum roughness in the mirrors. They're rough, certainly at that scale, if not at a bigger scale. Divide by 100,000, you get the diameter of the nucleus of an atom, 100,000 times smaller than the atom. Divide by 100, you get the magnitude of the motions that I was expecting that Ray would have to deal with in these instruments. It was obvious. There's no way this could work. Therefore, I called it not promising. And then I spent 2 years, not full time. I think you were, this is while you were a student at the beginning of this, or you were just finishing your PhD. And you're starting here. You started here in 74? Yeah. So this was basically when Bernie was starting here on the faculty. I spent some time during those 2 years thinking about this, studying Ray's technical paper, and being impressed by how he identified all the major noise sources you would have to deal with in these instruments and proposed ways to deal with them and made estimates of what kind of sensitivity you could achieve. And he seemed to have an argument that maybe this could succeed. Then I had long discussions with Ray, including one all-night session in Washington, D.C., when we were there for a committee meeting. We weren't very clear-headed for the committee meeting the next day. But we sat up in his hotel room all night long arguing about this. And then Vladimir Brzezinski, a brilliant physicist friend of mine in Moscow, Russia, again, extensive discussions with him. And I finally became convinced, and so I decided that this was so important in terms of the payoff that we might have, that I and my research group would do everything we could to help the experimenters pull this off. And Bernie made the same kind of decision here at Cardiff as we started to move forward, as did some of our other colleagues at other institutions. Some of the key experimental work developing this was occurring at Glasgow, and at Glasgow, Ronald Drever conceived an improvement on Ray Weiss's design. It would be much harder to make it work, but if it could be made to work, it would make these interferometers much simpler and more versatile. He said, let's have all of those light beams be on top of each other. There's no hole in the mirror, but you separate the mirror by a distance such that when light goes down and comes back, it travels an integral number of wavelengths, and so it superposes coherently on itself when it goes down and back. So the light can be trapped between the mirrors, but can leak out. And so the light goes in, it gets trapped, and then gradually leaks out. This is what's called a Fabry-Perot cavity. I don't want to go into the technical details, but it was a very clever but difficult to make work improvement. And I decided that and convinced my colleagues at Caltech that we should build a research group doing experimental work in this area. And so we imported Ron Drever to Caltech, initially half-time, so he was going back and forth between Glasgow and Caltech as we began to work on this experimentally at Caltech. Now I'm going to jump over a very long period of time. This talk is about more than gravity waves, okay? And I could happily give you a lecture for 15 hours about the history of gravity waves. But I'm going to jump over 40 years of intense work from 1975 to 2015. Experimental work initially at MIT, Glasgow, Caltech, and I didn't talk about it, but the Max Planck Institute for Quantum Optics. And then as time passed, other Max Planck Institutes, including the Albert Einstein Institute that Bernie was the founding director of, at the University of Hanover. And then groups in Italy and France, Japan, Australia, and then extending on elsewhere. So a huge amount of experimental effort over that time. Data analysis, pioneered here at Cardiff. Bernie claimed that I convinced him it should be done, it was doable. No, he convinced me it was doable. I may have told him it needed to be done, but he convinced me it was doable. And he and his group really laid the foundations and showed us how to go about doing the data analysis here at Cardiff. Computer simulations of sources. Bernie's group here at Cardiff did some of the earliest work on simulations of sources. And there now is back here another group within the Gravity Center that is continuing to do computer simulations of sources, led by Mark Hannum. And then LIGO, we finally, when things were sufficiently mature, we put together a LIGO collaboration, Laser Interferometer Gravitational Wave Observatory, led by Barry Barish, who was a superbly skilled leader of large projects, who knew how to organize things and make everything come together successfully. And he put together then a LIGO collaboration of 1,000 scientists and engineers at 80 institutions, 14 nations. It's larger than that now, but this was what it was by, I think, by 2015. So 2015, what happened? I'm going to tell you what happened by talking about the source of gravitational waves that we saw. 1.3 billion years ago, in a galaxy far, far away, two black holes circled around and around each other, and you can see them better on the side screens where the resolution is better. I'm going to turn the lights down also, because if I can do this right. Okay. So the two black holes circled around and around each other. They made these patterns, just like the patterns I showed you before, But now with them going around as more interesting patterns, Einstein rings that are more complex. And as the black holes circled around and around each other, they gradually lost energy to the gravitational waves, and so they spiraled closer and closer together, with gravitational waves getting stronger and stronger as they spiraled together. And those black holes, as they neared each other, they collided and merged in a gigantic cataclysm. The gravitational waves they emitted traveled out of the galaxy in which the black holes lived. They traveled into the great reaches of intergalactic space, across intergalactic space. They arrived at the outer edge of our Milky Way galaxy 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. They traveled for 50,000 years through our galaxy and arrived at Earth on the 14th of September 2015. 3 days before our first gravitational wave search with what we called our advanced interferometers was scheduled to start. These interferometers that by then had been built, they were very complex and they had to be tuned in many, many ways. And so the tuning was nearly finished, and this signal came in. And David Reitze, who was Barry Barrick's successor as director at that time, he declared the first search has begun because we saw something. And so the first search was off and running. The signal, when it came in, it went up through, let's go back, it arrived at the, down at the Antarctic Peninsula, traveled up through the Earth unscathed. Oh, where am I going? Okay, up through the Earth unscathed, and came out of the Earth at the LIGO gravity wave detector or interferometer in Livingston, Louisiana. And 7 milliseconds later, it came up out of the Earth at the LIGO detector in Hanford, Washington. This signal stretched and squeezed the mirrors, pushed them closer together and farther apart at the ends of these long arms. So the laser beams are inside pipes and bouncing back and forth, and the mirrors are at the ends and the corner of these arms. So the mirrors are pushed back and forth by the gravitational waves, and then the light recombined, as Ray Weiss had originally described, and that recombined light then had an intensity that went up and down, and that it was fed into a computer that analyzed the data, and the computer compared the oscillations with the predictions from computer simulations of colliding black holes. The LIGO collaboration, together with something called the Virgo collaboration, which was primarily at the time a French-Italian collaboration, which had also built interferometers of this sort, but their interferometer was not yet working. They participated in our data analysis. And so the two teams together, participating in the data analysis together, took 5 months to analyze the data and become totally convinced that this was really real. There were so many things that could go wrong that it was necessary to go in and study the signal and study the output from many auxiliary output channels. 100,000, there are 100,000 auxiliary output channels that tell you what's going on inside these complicated instruments in the environment. They studied the young members of the collaboration who really understood how these things work and understood the data channels. They went and they studied key ones among these many data channels to be absolutely sure there was nothing wrong and that this really was just caused by a gravitational wave. And then we announced the discovery. And when we announced the discovery, we, by comparing the signal cleaned up, in some sense, this is the cleaned up signal, is the gray oscillation. I'm plotting the stretching of the separation between mirrors up and the squeezing down in units of 10 to the minus 21 for this fractional stretching and squeezing. And the red is from numerical relativity simulations of colliding black holes. And by comparing with simulations for black holes of different sizes, different masses, it was possible then to determine that the source really was from colliding black holes. The initial black holes weighed 29 and 36 times as much as the sun, so that's a total of 65 solar masses. That just means that the gravitational pull was the same as that from a star that weighed 65 times as much as the sun. And the final black hole was 62 solar masses, and so 3 solar masses had been turned into gravitational wave energy. It's as though you had annihilated 3 suns and turned all of their mass into gravitational waves. And that happened in about 1/10 of a second, so the power output, the amount of energy 3 solar masses worth in a unit time, in a time of 1/10 of a second, turned out to be 50 times larger than the power output from all of the stars in the universe put together. 50 universe powers from 2 little black holes colliding for a short time, just 1/10 of a second. But it was the most powerful explosion that we ever had any evidence of except for the Big Bang birth of the universe. And we also, by comparing with the computer simulations, deduced that the distance to the source was 1.3 billion light years. When the result was announced, it made front page headlines in all the major newspapers around the world. Well, it's now several years later, and we're in the midst of our 3rd gravitational wave search. Between each search that's carried out, each search lasts for some months. The instruments are improved. They're shut down and they're improved for some months, and then it searches again. By now, more than 30 gravitational wave signals have come in. And there's an app you can get for a smartphone that's called GW Events. It's on my smartphone. And wherever I am in the world, and whether it's the middle of the night or the daytime, when a gravitational wave event comes in, within less than an hour of when it arrives, a signal goes off in my smartphone app. It goes whoop. It's a chirp. That's what the gravity wave signals would look like if you put them on sound like if you put them on a loudspeaker. And so there's a chirp, and then I can go in, and I can see, oh, there's a new gravitational wave signal in this list of recent gravitational wave signals. I want to go in and see what the details are, so I click on this to see what the details of this particular one were. This is one that came in September 30th of this year. So that's a couple of weeks ago. These detectors, the interferometer, shut down for the month of October for some small, minor improvements. What I'm showing you here is the events that came in the 2 months from late July to late September. There were 10 events. You look at these, and this is what you yourself can see. This is not me going in talking to my LIGO colleagues who are pulling this off. I'm not involved hardly at all anymore. It's this team of younger people who are superb that are pulling this off and have been responsible for the discoveries. But I can just go on my iPhone and I can see, like you can, there were 5 collisions of black holes in that 2-month period. 1 collision of neutron stars. The first collision of neutron stars that was seen, 2 years ago, was spectacular with electromagnetic emission. This one was not seen electromagnetically, partly perhaps because only 2 of the gravity wave of the 3 gravity wave detectors that we had at the time. By then we had a Virgo gravity wave detector operating, and so we had 3 of them at the time. But with 3 of them operating, you can determine fairly accurately where the source is on the sky. With 1 of them down, you don't get a good location on the sky. So it was harder to see it on the sky, and this thing was quite a bit farther away than the one that was spectacular. There were 2 cases in those 2 months of a black hole swallowing a neutron star whole. Each neutron star is about 30 kilometers across, made of almost pure nuclear matter, mass of about 1.5 times the mass of the sun, and no electromagnetic emission, and reason to believe that the neutron stars were swallowed whole by the black holes. And there were 2 black holes that swallowed something that we're not 100% sure what it was they were swallowed. And they're actually up here. They were both in late September. It's labeled mass gap. The point is that we think that neutron stars don't get heavier than 3 solar masses, And we've never, ever seen a black hole, despite huge amounts of astronomical observations, never seen a black hole smaller than 5 solar masses. So that's a mass gap where, and there were 2 signals, one with 100% confidence that it was a object in the mass gap. Here's the 100% confidence. It was an object in the mass gap. And the other 95% confidence. And so this is sort of a breakthrough. There really are compact objects like black holes. They probably are black holes, but nobody had ever seen a black hole this small. And so no technical papers written yet on any of these things. And there's a lot of really exciting science in here. But you can go onto your app and just see the basics of what is likely to come out in these exciting technical papers that are being worked on at the present time. By the late 2030s, 20 years from now, the successors to LIGO and Virgo, which are called Einstein telescope here in Europe, a large, new, much larger interferometer than what has been operating at the present time, and a similar, much larger interferometer called Cosmic Explorer in North America, will likely see gravitational waves that are maybe 20 times weaker than what is seen today. And that's really impressive. That means if the universe were infinite and flat, you'd be seeing out 20 times farther. You'd be seeing a volume 20 cubed times bigger. 20 times 20 is 400. That's 8,000, is that right? So 8,000 times more frequent events. Instead of 1 event a week, that's 8,000 events a week. Well, the universe is not flat, and it doesn't extend forever, so it's going to be a little lower than that. But nevertheless, an enormous number of events. Every black hole collision in our universe with masses less than about 100 solar masses is likely going to be seen at that time. A variety of other phenomena on the warped side of the universe. And also by the 2030s, we'll be seeing gravitational waves in 4 different frequency bands. LIGO and Virgo and their successors operate for gravity wave signals that have wavelengths of oscillation of milliseconds. LISA, a European Space Agency mission that you don't see so well here, let's go up here, consists of 3 spacecraft that track each other with laser beams. And we'll look at gravitational waves with periods of minutes to hours. There's a technique called pulsar timing arrays that I won't talk about at all. But that will see gravitational waves with periods of years to decades. And then a technique called CMB polarization I'll talk about very briefly, seeing gravitational waves with periods of hundreds of millions of years. Of course, that's a little longer than a graduate student lifetime. And so you don't sit there as a graduate student waiting for the signal to oscillate so you can get your thesis on it. Instead, you look at a pattern on the sky of what is called polarization of cosmic microwaves, a pattern that has been produced by gravitational waves from the very early universe, as I'll describe very briefly in a minute. So let me talk about this LISA mission. It's a really exciting mission. I think the science that it's going to do is more exciting than anything that has been done as yet with the ground-based interferometers. I have been hoping it would be launched by 2030, but Bernard says it's such a challenging thing that 2034, which is more likely for when it will be launched. And it's as I say, a European Space Agency mission. It will look for gravitational waves from giant colliding black holes with masses of millions of suns. Also particularly interesting to me is that a small black hole going around a large black hole will obviously create ripples in the shape of space, and those just become gravitational waves that go propagating out. And as was shown by a student of mine, Fintan Ryan, back in the 1990s, the gravitational waves from the small black hole as it's exploring space around the big black hole should carry a full map of the warped space-time of the big black hole encoded in these emitted gravitational waves. And you might ask, well, how can it possibly carry a full map, the warping of time, the warping of space, the dragging of space into motion? If it's just going around and around like that, how's it going to get enough information to make a full map? Well, let me get rid of the warping of space here and just pretend that space is flat around the big black hole. And then let's again look over here where we have more dynamic range on the screen. So the black hole is here. Maybe I'll turn the lights down also because it's a little hard to see. So the orbit of the small black hole around the big black hole is very complicated. It's nothing like these nice elliptical orbits of the planets around the sun. Why is it complicated? Because gravity is so weird in there. Gravity includes a warping of space, a warping of time, a whirling motion of space around the big black hole, and the gravitational pull. And even the gravitational pull is different than it is here on Earth. It's not an inverse square law, if you know that, the meaning of that jargon. It's more complicated. And so that gives rise to an orbit that basically samples the entire space around the big black hole and is capable of providing the data for a map. Now, it's a huge challenge with this LISA mission to extract the map from the data, and it's going to be but efforts are underway to develop algorithms to permit that to be done. So what if the central body is not a black hole? For example, what if it's, I said that inside a black hole there is something called a singularity. It's a place where gravity becomes infinitely strong and really weird in its properties. And the laws of general relativity get replaced, presumably by something called the laws of quantum gravity. It's conventional wisdom that singularities today exist only inside black holes. But what if you had a naked singularity? Well, here is a particular naked singularity in here, and an orbit of a small object, say a small black hole, going around that naked singularity. And the orbit is not at all like what we saw before. It's chaotic. It sort of has little jumps and jiggles. And it is chaotic in the mathematical sense of chaos, and quite remarkable. And obviously, the map that you would manage to extract from this, if you can extract the map, will be wildly different. So we have the possibility to search for naked singularities. This is one example of weird things that might be done. I'm particularly interested in the dynamics of the space-time geometry around colliding black holes. And we explore this by computer simulations, and then we compare the shapes of the waves that are come off in our simulations with what is seen by LIGO and Virgo in order to see whether or not this dynamics of warped space-time that we are predicting is correct. And we get very good agreements between the predicted wave shapes and what is observed. And so we believe that the true warping of space is what is predicted by the computer simulations. So this is a simulation showing the warping of space around then two black holes that are spiraling together. Each black hole is like a funnel in terms of the warping of space. The color coding is the slowing of time. I have to tell for the mathematicians and physicists, there's a slight cheat here. What we have is a two-dimensional surface in the orbital plane of the two black holes. Any two-dimensional surface can be embedded in a three-dimensional flat space. So that's what's being done here. The bulk that you're looking in from is a three-dimensional flat space. But that embedding can only be done locally. And so if you try to do it and you go around the black hole and you come back, the shape does not match up smoothly. And so there has been a kludge done here. I won't tell you what the kludge is, but there's been a kludge done here. But you can still take this seriously as representing, in some fairly accurate sense, the warping of space around the black holes as they collide. Now we're going to slow the movie down as the collision begins. You see there's a huge splash in the shape of space forming, like the splashing of the surface of the ocean in a giant storm at sea. And the color coding is the slowing of time. It oscillates wildly, settles down, and the gravitational waves go away. So this is what we call geometrodynamics, the dynamics of the highly warped space-time around two colliding black holes. And we've been learning about this from computer simulations. And particularly interesting, but I won't take the time to describe it, is what we have learned about how these vortices that stick out of black holes behave when the black holes collide. I want to wind up gravitational waves by briefly saying that one of the things the thing that I think is going to be most interesting with gravitational waves in the coming few decades is to observe the birth of the universe and the birth of the fundamental forces that govern the universe. As an example, when the universe was a trillionth of a second old, the electromagnetic force and the weak force came apart, gaining their own identities in what is called the electroweak phase transition. And so inside of this bubble, if this was as it could have been what's called a first-order phase transition, inside of this bubble, the electromagnetic force exists. Outside it does not exist. And in here it exists, outside it doesn't exist. The electromagnetic force was born. There was no such a thing as electromagnetic force before then. And these bubbles then are predicted to expand very fast and collide, producing a burst of gravitational waves. As the universe subsequently expands, those gravitational waves are shifted to longer wavelengths, and today they're in LISA's frequency domain. So with LISA, we hope to see the gravitational waves from the birth of the electromagnetic force when the universe was very young. We expect to see gravitational waves from the Big Bang. I'm going to go through this very quickly because I want to wind up with a few words about time travel and wormholes. But the basic idea is that something came off the Big Bang, and whatever it was, in terms of gravitational waves, was amplified by a process called inflation at the beginning of the universe that some of you are aware of. And these gravitational waves then, a very rich spectrum of gravitational waves that have then been amplified by inflation, they interact with a hot gas when the universe was about 380,000 years old, and they put this polarization pattern on the hot gas, which then astronomers have searched for. They have found this polarization pattern, but there is noise in the data, and they're not sure that whether what they've actually seen is due to the noise or whether it's really due to these primordial gravitational waves. That will get sorted out, I'm sure, within the next 10 years. And we then will have, today, we will have then indirectly, through this pattern of polarization on the sky, we will have then detailed information about the Big Bang singularity in which the universe was born, but mixed together with information about inflation, the very rapid early expansion of the universe, convolved together. I look forward eagerly to seeing this. There are predictions for what the result should be, and I expect the predictions will turn out to be wrong, and it will force the theoretical physicists to go back to the drawing boards. And then in the middle of this century, there is likely to be a successor to the LISA mission called the Big Bang Observer, which will see these primordial gravitational waves with periods, instead of hundreds of millions of years, periods of a few seconds. Radically different periods. And again, just from past experience, I'd be surprised if the theorists have it right when they predict what is seen. Okay, I want to conclude with a few words about wormholes and time travel. I think a lecture on what we have learned during my career would not be complete without saying something about this. And I think many in the audience are probably eager to hear what we have learned. So wormhole. Suppose that our universe in the bulk is bent around like this. This is a two-dimensional slice through our universe, like I was doing for the equatorial slice through a black hole. It's bent around so that our solar system over here, and in particular Saturn, is only a distance of a few kilometers away from some galaxy in the very distant universe. So if we travel out through the universe, it may be 10 billion light years to the solar system from there. But across the bulk, it may only be a few kilometers if we could travel across the bulk. But we are three-dimensional beings. We have three space dimensions, two if I've removed one like this. And we can't live in the bulk. The electromagnetic force that's crucial to our existence and our life can't even exist in the bulk, and it can only exist in three space dimensions, two if I've suppressed one like this. And so in order to go across the bulk, we need to have a structure, a wormhole it's called, like that, where you could travel then along the surface of that. The surface looks two-dimensional, it's really three-dimensional, to get from our galaxy to this distant, from our solar system to this distant galaxy. In the movie Interstellar, this is what happens. bulk beings that live in the bulk have provided to the human beings in this movie that I worked on, have provided to human beings a wormhole of this sort. Eugenie von Tunzelmann at Double Negative in London and a set of painters associated with her made paintings of the center of this galaxy that is on the other side of the wormhole. I worked out the equations for the propagation of light beams from that galaxy through the wormhole up to the camera. I fed them to Oliver James, whom I have mentioned before, who is the chief scientist at Double Negative, and he then programmed those to make a movie that I'm going to show you of what it looks like to go through a wormhole. So this is what the wormhole looks like in the movie Interstellar, for those of you who've seen the movie Interstellar. For the movie, I'm going to move the wormhole up almost in front of Saturn. So Saturn is very far away. The wormhole is only a few kilometers across, and Saturn is very, very far away. And so it looks about the same size as the wormhole. Light rays from the Saturn bend around the wormhole to produce this image, and bend around the wormhole on the other side to produce that image. And if I now start to travel into the wormhole, the images of Saturn are pushed apart as I go into the wormhole. I'm entering the wormhole now. I'm traveling through the wormhole, and I've come out the other side. That's what it really looks like for the wormhole in the movie Interstellar. I had a telephone call from Christopher Nolan, the director of Interstellar, when he first saw this trip through the wormhole. They were in the process of starting to integrate the computer graphics into the film. He had just finished shooting all the human action. He said, "We've got a problem. Would you come over to my house? I want to talk about it." And so I went over and he said, "Look, this is not exciting enough." And we had agreed, I'd happily agreed with him, that, and he'd agreed with me, that we would do everything we could to make all of the movie be scientifically accurate to the extent it did not get in the way of making a great movie. And this is the one place where we compromised, or where we had a significant compromise. So what did I say to him? I said, "You use artistic license." And so that's not the trip you see, though it resembles this, but there's a lot of artistic things stuck on top of it. But this was the real trip through the wormhole. Now, the problem with wormholes is that, as John Wheeler, my PhD advisor, showed back even before I was his student, together with a young colleague, Martin Kruskal, a wormhole will pinch off if you don't do something to hold it open. So if I have a particle of light, a photon, trying to travel through the wormhole to bring me an image, and the wormhole is just empty, sitting there with nothing except, say, a bunch of light traveling through it, then as the light travels through, just at the moment that the photon reaches the center of the wormhole, it pinches off, and you're left with two naked singularities, and the light has been destroyed. So you can't get the light through, and you can't get humans through. So there's the issue of how can you hold a wormhole open? Well, various people have worked on it, and we now know that what you have to do is stick inside it something that repels gravitationally. That's pretty obvious. The walls need to repel each other gravitationally. And that means you have to have something with negative mass or negative energy. And in fact, and so you would say game's over. How can you have negative energy? And the answer is you can have it. And just for physicists, the Casimir vacuum and the squeezed vacuum. You have some squeezed vacuum. Do you have squeezed vacuum here in your new lab now, or you're just going to have it? So there's a plan to have squeezed vacuum in the lab if they don't have it already. And so they're going to be making negative energy matter here, exotic matter. But the problem is, I'll tell you what the problem is in a moment. So can wormholes occur naturally in the real universe? The answer is almost certainly no. These are answers that a number of people have struggled to understand. And this is the bottom line after several decades of trying to understand it. Can wormholes be made by an advanced civilization? Possibly. It's quite possible, as John Wheeler told us, that down on very, very tiny scales of 10 to the minus 33 centimeters, called the Planck length, that there is a foam of tiny, tiny wormholes that's just bubbling and bubbling and bubbling quantum mechanically. And so you can imagine a very advanced civilization reaching down and grabbing one of these wormholes and enlarging it, making it big so you can travel through it. It's pure imagination. It's something you would do if you're a physicist when you're very, very drunk, to speculate about this. But I don't think it's totally out of the question. If you do have such a wormhole, can it be held open? The answer is probably not. And this is where a lot of work has been done, because it appears to require too large amounts of exotic matter, of gravitationally repelling matter, negative energy. But when speculating beyond the frontiers of firm knowledge, I've been proved wrong many times, sometimes spectacularly, so you don't take my pronouncements that you can't have wormholes too seriously. And I was willing to use it in the movie Interstellar. Finally, a few words about time travel. This is from a technical paper that I wrote with two students of mine, Mike Morris and Ulvi Yurtsever, in 1988. Suppose that my wife, Carol E. Winstein, has one mouth of a wormhole, and she's in this rocket ship, and I'm back home with the other mouth of the wormhole. And she goes out. She has a very advanced technology. She travels out at close to the speed of light, turns around, and comes back. Now, there's something called the twins paradox, which says that she will age much less than I do. She may have aged a few hours or a few months, and I may have aged a few years when she goes out and comes back. And so I'm an old man, and she's still quite young, as we see each other looking through the external universe. But if we're holding hands, and I look at her wristwatch, and she looks at my wristwatch inside the wormhole, they have to tick at the same rate inside the wormhole. This is what the prediction is. And so looking through the wormhole, she sees me young, because she's young, and our watches have been ticking at the same rate. But looking out through the external space, she sees me old. So she returns back to Earth. And so these wormhole mouths are here almost side by side. And so all I need to do as an old man is go and enter that wormhole and go back and meet my younger self, because I can see my younger self through that wormhole mouth. So it's easy to turn a wormhole into a time machine if you have a wormhole. Well, not technologically easy, but relativity seems to allow it. The problem is that relativity, which seems to allow it, is not the only set of laws of physics that we have to deal with. We also have to deal with the quantum mechanical laws of physics. And quantum mechanical laws of physics, when you look at them, they seem to say that whenever any advanced civilization tries to build a time machine, the time machine will have a gigantic explosion at the moment it's turned on. And in this case of this particular time machine, the key issue is that if you imagine she's traveling back toward me, and there's a first moment when something could go down through the wormhole, out my wormhole, travel back, and return at the very moment that it started out. And so you have two of them. So these might be photons, particles of light, go through the wormhole and then back out the exterior region. You began with one photon, you now have two. They're the same photons, but they're side by side. Then the trip is made again, you now have four photons. They're the same photon, they're side by side. You have a huge burst of energy going through the wormhole at the moment that this wormhole turns into a time machine. Well, you can shield out photons, but you cannot shield out something called vacuum fluctuations. And these things, which are also called virtual photons, these things which play a huge role in modern physics and experimentally, manipulating this vacuum, which I'm not going to go into, is the key to making this squeezed stuff that is going to be made in the laboratory here that has negative energies. So these vacuum fluctuations can do this, and you can't shield them, and so there will inevitably be an explosion. And so I found this with a postdoc of mine in a calculation. And then some colleagues of mine, and here's a technical paper, did a far more rigorous calculation that showed the same kind of a thing, but not showing any details of the explosion. So I think this is incontrovertible, that there is some sort of something really goes wrong the moment you make a time machine, try to make a time machine. But what we don't know is whether the explosion then is strong enough to destroy the wormhole. And Stephen Hawking was working on this at the same time as I was. Stephen is one of my closest friends, and we never collaborated together, but we worked at the same time on this problem, and we argued back and forth. And ultimately, we came to agree that we can't tell whether the explosion is strong enough to destroy the wormhole. Only the laws of quantum gravity, which we don't understand, know whether it will destroy the wormhole. The laws of quantum gravity govern the birth of the universe. They govern what goes on inside black holes. And they seem to govern whether or not time machines self-destruct. Stephen then proposed the chronology protection conjecture because he was so sure that the explosion is going to be totally destructive, that the time machines will always self-destruct when you turn them on, keeping the universe safe for historians. And that's his phrase in this technical paper, whose title is the chronology protection conjecture. So I was working on this at a period just before we got approval to construct LIGO. And when we got the approval to construct LIGO, I left this all behind because LIGO got very exciting. And I've not had a chance to return to it. But it's quite interesting that you see these weird kinds of things coming out of warped space-time, just like gravitational waves and black holes. So conclusions. When I was a student, there were speculations about the warp side of the universe. Today, 57 years later, we know a lot more. We have observed black holes. We have observed gravitational waves. We have a lot of observational evidence about the Big Bang. We doubt that wormholes exist and doubt that backward time travel is possible, but we're not absolutely sure. And in the future, I believe gravitational waves will reveal a great deal about the warped side of the universe. There will be enormous surprises of which we can't even dream today. Thank you.